Hello everyone and welcome back to your YouTube channel and welcome to this very exciting example today. As you must be aware, I am recording this series of videos related to fundamental of power engineering. And in this video today, I have a very quick but very interesting tutorial, and it's a numerical solution for a basic example of three-phase system. In particular, today we are dealing with this example where we want to calculate the quantities, electrical quantities in this three-phase system. So let's start with this. The figure Q1 that is over here below shows a 208 volts line-to-line RMS voltage three-phase ideally balanced system. What I am telling you is that this is a three-phase system that we know that is balanced. You can see over here voltages, magnitudes are the same, and also this is symmetrical because you can see that the impedance in each one of the phases is the same. So the first question is quite interesting, very simple, but it's very relevant for you that you are learning about three-phase systems. So as you can see, the first question is calculate the magnitude and angle of the line current in phase A. And we want this current in amps. So if you look here, I am using this red arrow over there in order that my students can easily highlight the location of this line current, okay? Then there is a question B, and we want to calculate the magnitude of the load, line, and phase voltages, VLL and V phase L. So if you look over there, wow, it's very simple. You can see very simple the location of these voltages over there. So let me use this yellow highlighter. So you will see over here that the line-to-line voltage is located over here. This is VLL, and in this case we are representing the voltage between A and C. And over here you can see this is the location for the voltage, and in this case this is between A and N. So it's very important for my students that they clearly identify that when we are between B and C, this is a line-to-line quantity. When we are between the line and neutral, this is a line-to-neutral quantity, okay? So this system is very, very simple but very useful, because in the future you will understand that this representation over here, you can imagine that this is an ideal AC generator. On the right hand side, you can imagine that this is basically a three-phase load, and you can see that this is a constant impedance load. And the reason is that you can see that we are using a resistor, 12 ohms, in series with 9 ohms, and that is the inductive reactance. So between the generator and the load, there is a series impedance, and that is basically, you can imagine that as the impedance that is connecting the load and the generator. So this can be, for instance, the series impedance of the cables, and this connection is series, okay? I need that all my students can see that here we have a star connection, and the easy way to understand that this is a star connection is because there is a neutral point over here, and on the right hand side, again, this is the load. You can see below, this is the load. And you can identify that this is a star connection because you can see the neutral point over there. So finally, be careful because don't make the mistake. This is series connection, okay? So very important for you, please pay attention to the subscript, because L to L represent line to neutral, and the other one represent the phase voltages or line to neutral, okay? And also solving this problem is extremely easy, because this is a beautiful three-phase system. This is a beautiful three-phase system, and this system is balanced. So we have three phases in this system, but we can take advantages of the three-phase properties. So we can create a equivalent circuit, and this equivalent circuit will be basically a representation, line to line representation of the phase A. So let me go back here a bit so you can see the following. How do I obtain this figure A? This figure A here below is basically the single phase equivalent circuit, but that is obtained from here, the three-phase circuit. How do we obtain that? Well, it's very simple. We start here from the phase A, we move around from the series impedance, and we arrive here to the label 8. Then we go to the neutral point, and from the neutral point, we imagine that we can travel here to the neutral point back. And finally, we move across this voltage source. So if you follow my explanation, in other words, I am taking the neutral, moving around here to A, pass through the series, and then going through the load and arriving to the neutral point. So this model received the name, this model is very useful, and this model is called the per phase equivalent circuit. Also some books, and I prefer this name, single phase equivalent circuit. What is this circuit? Well, this circuit over here is the representation of one of the phases inside the three-phase system. And we can use this and we can do that because there is something that is called three-phase symmetry. So working out the solution of this problem in one of the phases will give me the results that I calculate the other phases, okay? So the next step is, well, now we have a circuit. Now you can apply everything that you know about circuit theory. So the interesting part over here is that I can use Ohm's law over here and Kirchhoff voltage law. So if I use Kirchhoff voltage law, if I use this Kirchhoff voltage law in this very interesting loop here, so the voltage at the voltage source, it will be equal to the voltage drop here at the series impedance. And using Ohm's law must be the series impedance multiplied by the current plus the voltage drop through this load. And this is the load impedance multiplied by the current. So next step is we calculate the series impedance, the equivalent impedance that is basically series plus the load. So the series impedance is very low, 0.6 plus J 0.12. And the load impedance is a bit larger. You can see over here, 12 ohms plus 9J ohms. So for you, it's very simple. Here, this is the rectangular form. You can see that the rectangular form is 12.06 ohms plus 0.12 J ohms. So it's very simple. So the next step, my dear students, the next step is, obviously, if we have an equivalent impedance, we can calculate here the current in this circuit. We can extract from here the current, and it's basically the voltage, in this case 120 degrees, divided by the equivalent impedance that we already calculated here. So we obtain the line current. The line current is the current that is moving over there. You can see clearly that that is the line current. The line current is moving through the series impedance over there. You can see clearly. So we obtain here, let me show you the numerical value. You can see that the numerical value is 7.93 at, this is the angle, minus 37.09 degrees. Okay? So what is the next step? Well, my dear students, that is only for the phase A. So we have this current over here. This is the one that I obtained. This is the one that I obtained from the single phase equivalent model. But if I want to know also B and C, what I need to do is basically apply three-phase properties. And as you can see, we assume that the voltage is reference. You can see that this current is located at minus 37 degrees. So B and C, they can be easily located because they are 120 degrees. And in this case, is negative in this case, minus 120 degree between A and B. And between A and C, they are 120 positive. So what we are doing is basically, okay, let me multiply the current that we already know, and that is the current in phase A. We multiply by 1 and the angle minus 120. So as you can see over here, the magnitude 7.93, and you can see the angle minus 157. So it's clear here in this graph, that the location of the phasor representing the current on phase B is located at minus 157 degree. Similarly, we can use here the same approach for the current on phase C, and we are multiplying by 120 degree positive. So now you can see same magnitude, 1.93 amps, but the phase angle, as you can see over here now, is 82.090 degrees. So again, my dear students, what I want is that you reflect about the location and the phase angles between the voltages and the currents ABC for this circuit, okay? I highly suggest always, my dear students, that you create this representation. This representation is the phasor diagram. Phasor diagrams will make your life easy. They will allow you to see graphically the possible solution, and that will make your life extremely easy. So next step, continuing with the solution, the next step is, well, we want the voltages. We want the phase voltage, and the phase voltage, you must remember that is basically the voltage drop. Let me go to the equivalent circuit here. Basically, we want the phase voltage, and looking into the single phase equivalent model, this phase voltage over here, is basically the voltage across this load, and that voltage can be obtained using the classical Ohm's law. Ohm's law say, multiply this impedance, multiply by the current. So we multiply the current on phase A, 7.93 minus 37 degree. We multiply by the impedance, 12 plus 9J ohms, and we obtain this beautiful voltage over here. As you can see, the voltage over here is 119.04, and the angle is minus 0.22 degrees. It's very important that the students include this remark over here. This is a line to neutral voltage, and this is a polar representation or polar form. Finally, we want to calculate the line-to-line voltage. And to calculate the line-to-line voltage, remember the line-to-line voltage is here in the main circuit. Here you have the line-to-line voltage. And to calculate the line-to-line voltage, we apply a very useful property. We discussed this property during our theoretical classes. And the line-to-line voltage is related to the line-to-neutral voltage because the magnitude is amplified square root 3 times, and the angle, the phase angle, is modified by 30 degrees. So what we are doing is square root times 119 volts, and the phase angle is moving from 0 to 30. So because we are adding 30 here, remember 30 minus 0.22, that is 29.77. So this is the line-to-line voltage. Remember, my dear students, I always suggest to include the remark about this is the line-to-line or the line-to-neutral quantity, okay? Finally, a short reflection over here. I know this voltage is correct because if we are using a delta source, a star connected source, always the voltage will be larger, the line-to-line voltage will be larger than the line-to-neutral. And in this case, you can see it's evident. You can see that 206 volts are larger than 119. Finally, before we finish this very exciting video today, so I will invite you, please go to my GitHub repository, because over there you can find this very interesting and very simple MATLAB code. And with this MATLAB code, running this MATLAB code, you will be able to replicate all the numerical solutions that we study over here. So please go over there, and have a look and use that MATLAB code, because also I am really interested that my students also, they have a basic understanding about programming, okay? So we are reaching the end of this video. As I always say, this video is created using some of my personal documents. I created the original documents around 2007, probably many years ago, but this document is available for you at ResearchGate. And for the MATLAB code, remember, please visit here, visit the GitHub repository, okay? So please, I hope you enjoyed this amazing video today. It's a numerical example. And please, if you like this video and you want to watch more about this, please feel free to drop a comment in the video at the YouTube channel. But also, if you want to subscribe to the channel, that will be even better, because you will get access, instantaneous access to the most recent videos, and you will receive notifications about the community and what we are doing. So this is the very end of this video. I would like to say you thank you very much for watching, and I will see you at the next one. Bye now.